hope we're ready. I hope we are ready. All right, we're live. We are live. Tomorrow, 8 a.m., Blue Gym. Scientific calculator, no graphing. If you don't have a scientific one, you're getting a blue one. You need a pen. You can bring a pencil, but all your answers need to be in pen. That's about it. Other than that, you got to bring your brains. You got to bring your chemistry knowledge. You're going to kill it. I'm going to wait a few minutes to get going here. I just sent the link out on Remind. And we will get started shortly. Basically, goal for tonight is I'm going to go over pretty much as slowly as I can very popular questions out of every single Regents, or as much as I can get through in these review books. I've already done 2013. I went through 2014 pretty much last night. I've done my part. It's your turn to step it up. Try to get your goal. Try to achieve your goal. Hope you're ready. Um, 8 a.m. Blue Gym. Pen. Scientific calculator. This is definitely going to... Already, the amount of people logging in right now is the most out of all my live streams. Nothing like a little last-minute cramming the night before. Let's learn all of chemistry in under 12 hours. Or in about 12 and a half hours. Because it's at 8 a.m. tomorrow. So, I'm going to wait a couple minutes. Let people to start kind of slowly walking in. I'm going to go over... Not every question, don't have the time for that. But I'm going to go over a bunch of popular / difficult questions out of as many Regents I can get through in your green review books. As I'm sliding down here, I'm going to go slow. But if you see a question pop up and you're like, whoa, Mr. G, can you go over that one? Sure, just text me on Remind. All right, hold on. So, right now, the Regents I have queued up, and I know we took this Regents already, but it's good to review. It's not like you're going to remember the exact question. Is the first Regents in your review books, these green review books. Got these like probably over a month ago at this point. We're going to go through as many as I can get through of the most popular questions, the most difficult questions. And I'm going to scroll slow. So just feel free to stop me. Even as you look through this book and you read a question that you already answered and it's like you didn't change it, you probably got it right, and you're looking at it and you're like, what the heck? Why did I put 3? Is this right? Why? I don't remember why. Oh my God, just text me on Remind. Type in the chat here. If you have a Twitch account, feel free to type in here. Send me a text on Remind. Just say, hey, can you go over number 3? I know you didn't go over number 3, but can you go over number 3? The answer is going to be yes. An emphatic yes. We're going to get started in a minute. Thank you to everyone that came to the review session at 3 o'clock today. Appreciate it. 8 a.m. tomorrow, Blue Gym, scientific calculator. Don't bring a graphing one. If you bring a graphing one, you're going to be handed one of those terrible blue calculators. Pen. no pencil. Pen, please. You can bring a pencil. But all your answers need to be in pen. We're going to start off tonight with a request. Can you do a drawing of an atom and an ion? You got it. So let's go to the periodic table. Let's just pick, let me just do a little erase in here because I've done so many live streams. Let's do oxygen. All right? Let's do an oxygen atom. Come on, Mr. G. You can do this. Let's do an oxygen atom versus an oxygen ion. So first, oxygen atom means draw oxygen as it exists normally in its ground state. And when you look at oxygen, it is 2-6, which means it has 6 valence electrons. So a good old-fashioned oxygen atom is going to be 1, 2, 3, 4, 5, 6. An oxygen ion means take that same oxygen and draw it with its charge. An ion means the atom has become charged. An oxygen's charge is -2. A negative charge means you are gaining electrons. I know that's confusing because you see a minus sign and you want to say it's losing, but you got to remember, protons are positive, electrons are negative. So, oxygen with a -2 charge will have 1, 2, 3, 4, 5, 6. -2, 7, 8. Put the charge on it when you're done. That's the main difference between drawing an atom versus an ion. Typically, you're not going to be asked to draw individual positive ions. You're usually going to be asked to draw ionic compounds. So, for example, if you were asked to draw the ionic compound NaCl, you would look up Na in its ground state. Na in its ground state is 2-8-1, which means an atom of Na would have 1 electron. Chlorine in its ground state is 2-8-7. So chlorine in its ground state would have 7 electrons, 7 valence electrons. Now, since we have a metal and a nonmetal here, this is an ionic compound. And ionic compounds, by definition, transfer electrons from the metal to the nonmetal. So, while these things currently separated from each other are not charged, when they are bonded together, they become charged because that sodium is going to donate an electron to chlorine, therefore becoming a positive charge, surrounded by no more electrons because you've donated it out of its last shell. And then chlorine gains an electron, and sometimes we signify that gain by drawing an X, and make sure you put its charge of -1. You don't really have to show the brackets, but we encourage you to draw ionic compounds with brackets so that we understand that this area in the middle doesn't have any electrons being shared. Shared electrons is what happens in a covalent bond, which is between 2 nonmetals. So, when you have a metal and a nonmetal and you're asked to draw it, I would check their charges. Na is +1. Chlorine is -1 when it's bonded with Na. I know you're going to say there's other charges there, but ionic compounds, opposites attract. If there's only 2 of them, one must be positive and one must be negative, because the total charge needs to equal 0. Since sodium is going to become positively charged, I would draw it without any electrons and with a charge of +1, because that 1 electron that it did have in its valence shell, it donated to chlorine, who now has 8 electrons, meaning it's gained that 1 electron because it's normally going to have 7 valence electrons, and when you gain an electron, you become negatively charged. All right, got another text on our mind. Yes, we are super positive that your test tomorrow is at 8 a.m. It's in the blue gym. Get there early. Let's say 7:45 a.m. Bring a pen, bring a calculator that's not a graphing calculator or one that can connect to the internet. So, just bring a scientific calculator. If you don't have a scientific calculator, you'll be given a blue one. If you show up at 12 p.m., you'll be taking the physics Regents. Don't show up at 12 p.m. Show up at 7:45 a.m. Okay, back to the Regents. So I'm actually going to start with number 1 because sometimes this phrasing, equal in magnitude but opposite in sign, is a little confusing. So we're comparing something to an electron. And when it says it's equal in magnitude, that means the size of the charge is the same. It's just that the sign, one being positive and one being negative, is opposite. So the charge of an electron is -1. So we're looking for something that's equal in magnitude, 1, but opposite in sign, positive. So we're looking for something that's charged +1. Neutrons are neutral. If you check table O, you'll notice that a beta particle has a -1 charge. An alpha particle is just a helium nucleus, so its charge is +2 because it has 2 protons, leaving us with proton. Got a couple more texts. Can you go over the history of the atom? Sure, I'll do that right now. Where's the PowerPoint with good vocab to look at? So, it's not a PowerPoint, it's a Quizlet. And I sent it out on Remind yesterday, so thanks for reading those. And it's on my teacher site. So if you go to my Saratoga teacher site and go to Regents Review, it's the first link at the top. Let me respond to this student. All right, history of the atom. Let me just start a new note here so I have some room. May or may not be a question, but still a great question to ask. In order from oldest to most recent, we have the people are Dalton, Thomson, Rutherford, which is the one, if I'm going to pick any one that they like to ask the most, it's Rutherford, Bohr, and then the last guys are like de Broglie and Schrodinger, but their names end up not really popping up in the Regents curriculum. So we'll just say the wave mechanical model. So I'm just going to give you some like buzzwords with each of them so you can just remember it quickly. Dalton, the oldest model, he believed the atom was a hard sphere, like a billiard ball. He didn't really have any understanding of like what the protons, neutrons, or electrons were doing. He just thought that they were like a billiard ball, just really tiny. Thomson, so next one, J.J. Thomson, he discovered the electrons using cathode ray tubes. So what he kind of noticed is that these negatively charged electrons were kind of attracted to positively charged things. So he's like, I'm going to call that thing an electron. His model was called the plum pudding model. I think it's more appropriate to call it the chocolate chip model. So he kind of just believed that the protons were just kind of scattered around the atom, kind of like chocolate chips in a chocolate chip cookie. Or sorry, the electrons were. I take that back. That the electrons were just kind of scattered around the atom, like chocolate chips in a chocolate chip cookie. So he thought that the atom was this one big, giant, positively charged thing with these chocolate chip electrons just kind of in there. Rutherford was the gold foil experiment. And what he discovered was that the atom was mostly empty. So the atom is empty, but there is a dense nucleus in the center. So He fired alpha particles at a piece of gold foil, and he realized that most of them just passed straight on through the atom, but every once in a while one would bounce off of something, so that led him to conclude that there's got to be something in the middle of that atom that he called the nucleus, but that most of the atom was empty. Bohr is the planetary model, so he has the nucleus in the middle, and it's surrounded by electrons that orbit that nucleus. He was the one that started to propose how electrons are involved in atoms emitting light. So when electrons move from the excited state to the ground state, atoms will emit different colored lights. He was kind of the first one that started to propose that idea. The wave mechanical model, pretty much all you need to know about that is that started to prove that electrons actually don't orbit the nucleus like a planet. They kind of exist in this area that we call an orbital. So when you see orbital, you think location of electrons. And that is the history of the atom. Dalton was hard spheres. Thomson was the guy that discovered the electron using cathode ray tubes. Rutherford did the gold foil experiment, and he discovered that the atom was mostly empty with a dense nucleus in the middle. Bohr was the one that proposed the planetary model with electrons orbiting the nucleus, and they exist in certain energy levels. They will emit light as they move from the excited state to the ground state. I guess another quick thing to add about Bohr was he stated that electrons closer to the nucleus, so closer to nucleus, so let's say the first shell, has less energy than electrons further away. And this was a good question asked today, and actually this is reminding me of another good question asked today that I'm going to go over after this. You would think that the electrons closer to the nucleus would have more energy, but in fact, since the nucleus is positively charged and electrons are negatively charged, they want to be close to the nucleus. So the ones closer to the nucleus don't really contain as much energy because they want to be there to begin with because opposites attract. The ones further away, let's say as you go from the second to the third to the fourth shell, have more energy because they're breaking that attractive force that wants them to be closer to the nucleus. Okay. And then he did the excited to ground state stuff. Electrons move from excited to ground state, and they emit different colored lights. And then finally, you have the wave mechanical model, which basically just states that electrons exist in these probable regions that we call an orbital. Okay. I got a lot of questions on Remind. I'm going to table that for a sec because I really want to go over this one other thing before I forget because it was a really good question. So, it wasn't this exact question, but it was about this diagram. This was a nuclear reaction, and we know it's a nuclear reaction because we have uranium going in and then two different nuclides popping out. So that elemental uranium transmutated or transformed into two different elements. So the key word here is transmutation. It's one word. I just ran out of room. So the key word here is transmutation. The issue that came up today was a lot of students were applying the BARF acronym to what's going on in this diagram. BARF is what you apply to questions like, and I know it's going to be in here somewhere, so just bear with me for a sec while I find it, because they pretty much ask it every year. BARF is applied to a question like number 9. BARF stands for breaking bonds absorbs energy, releasing energy forms a bond. So in this case, like number 9, what occurs when two fluorine atoms react to form a fluorine molecule? So we got two fluorine atoms combining to form a fluorine molecule. So do some process of elimination first before you do BARF. Remember, you have 3 hours to take this test tomorrow. That's a lot of time. Don't rush. So I see a bond is being formed here because two atoms are becoming a molecule. Then you would apply the BARF acronym. Breaking bonds absorbs energy. Okay, we know we're not breaking a bond. Releasing energy forms a bond. So the correct answer here was 4. Now, why can't we apply that to this diagram? You look at this diagram and you're saying to yourself, well, I see a uranium atom breaking apart. So there's 2 reasons why. The BARF acronym is used for chemical changes only, meaning reactions where the atoms on the left side and the right side remain the same. They just form different compounds on the left and right side. This is a nuclear reaction. Nuclear reactions involve an atom either spontaneously or artificially decaying into totally different atoms. So the BARF acronym doesn't apply because this is not a chemical reaction. In addition to that, technically, there's no bonds breaking or bonds forming in this reaction because that is an atom of uranium. It is not bonded to anything. It is just pure elemental uranium. No bonds here. So we can't say a bond's being broken because you're literally splitting apart the nucleus of a uranium atom. You're not doing anything with the electrons. So be careful with the BARF acronym. It's only for chemical reactions, not nuclear. When you see a reaction like nuclear, energy will always be released. So for nuclear reactions, energy is always released. And that's because these reactions are taking small amounts of matter and converting it into large amounts of energy. Just think of the atomic bombs. The atomic bombs were fission reactions occurring in a controlled environment and then detonated to cause some mass destruction. Hydrogen fusion bombs are the same thing. They create gigantic explosions. So they're always going to release energy, and they will always release more energy than any chemical reaction. All right, give me a quick sec. I got a bunch of texts on my mind, so I just want to look over some of them. First question, what are the patterns for ionization energy, electronegativity, and atomic radius in regards to groups and periods, and what table can we find that on? So, great question. Let me find an example question in this Regents. I'll go over all of them, don't worry, but they do ask those trends questions a lot. So for example, actually, I don't think that's going to end up being a good one. If I don't find one, I'll just go straight to where to find it, or I'll just make up my own question orally and then show you how to do it. Okay, so I can't find one quickly, so let's make it up. Let's say you had a question that asked you to state the trend in, let's just say all 3. Why not? Let's kill 3 birds with one stone. What is the trend in atomic radius, electronegativity, and ionization energy for the atoms in period 3? So first, periods here is when you look at the periodic table from left to right. Groups is when you look up and down. You can memorize the trends. So the period trends from left to right are electronegativity goes up, ionization energy goes up, and atomic radius goes down. But let's say you get into the test tomorrow, your chemistry teacher has told you a billion things to memorize, and you're like, I can't keep all this stuff straight. No worries. What you can do is you can pick 2 elements in the period, and I always recommend you pick the one in group 1 and the one in group 17. So in this case, sodium and chlorine. And the reason I say that is because when we go to table S right now, the atoms in group 18 don't have an electronegativity listed, so sometimes students get confused. So when you're doing these trend-based questions, I would ignore group 18. So let's go, I didn't need to back out, don't know why I did. Let's go to table S, And let's look up the electronegativity, the atomic radius, and the ionization energy for the first one in period 3, which is sodium, and the last one we chose in period 3, which was chlorine. And let's just see what happens to their trends. Sodium's, let's see. Ionization energy is the first one listed. Sodium's is 496. Chlorine's is 1251. Okay, so the trend in the periods is that ionization energy is increasing. Sodium's electronegativity is 0.9 and chlorine's is 3.2. All right, so we're confirming what I just said. The electronegativity in the periods is also increasing. And then sodium's atomic radius is 160 and chlorine's is 100. So again, we confirmed that the atomic radius was decreasing. You can do the same exact thing I just said for the groups. So let's say it was asking for the trend in group 1. Why do I keep backing out? Let's say it was the trend in group 1. Let's just stick with sodium because it's right there and we already looked at all of it. But now pick something in the same group. Let's say K. Let's look up, I did it again. Let's look up the group trends. So sodium's ionization energy is 496. K's is 419. Okay, so the group trend right now is it's decreasing for ionization energy. Sodium's electronegativity is 0.9. Potassium's is 0.8. Again, we're confirming that the electronegativity of the groups is decreasing. And then sodium's atomic radius is 160. Potassium's is 200. Okay, so the trend for the groups is the opposite. The ionization energy and the electronegativity decrease while the atomic radius increases. Okay, next. Do we need to know that? So the atomic history I just went over, do we need to know it? There are years, literal years, like June 2015 through 2017, where table H might not even pop up on the Regents at all. I can't predict what types of questions they'll ask for atomic structure, or I should say I can predict what types. I can't predict which ones they'll end up selecting. You can write a whole 80-question test on just atomic structure. It's just how our chemistry curriculum in New York State is. It doesn't go very deeply into the chemistry. There's not a lot of depth to it, but it's a lot of information. So, will history be on the test? I have no idea. 2 years ago, they didn't even ask a question on significant figures. So again, I can tell you the types of questions they might ask. I cannot tell you the types of questions they will ask. So, play it safe. You might need to know it. A bunch of thank yous, a bunch of thank yous. When does MAVA equals MBVB come into play, and how do I know when to use it? So, great question. MAVA equals MBVB is this equation right here. The first thing you should have in the back of your head is you kind of look at the A's and the B's, and you're like, okay, it's something with acids and bases. So I already have in the back of my mind, when they ask about molarity of an acid or a base, or the volume of an acid or a base, I'm probably using this equation. But let's see it in context. Let me find one. I know I am fairly certain there's one every single year on the Regents. I just need to find it. Hopefully. They're usually short answer questions. That's why I'm just kind of skipping around. So just bear with me, please. So, MAVA equals MBVB. How do I know when to use it? Oh, come on. You got to be on here somewhere. Watch, every year for these 4 Regents exams, they're multiple choice questions just to make my life that much harder. Come on, come on. Where are you? Where are you? Oh my god, yeah. All right, now we're on the 2018 exam. Were they all multiple choice questions the past 4 years? I don't have that good of a memory. I know they asked about it. Come on, don't let me down. Please be on here so I can help my student. Here we go. Okay, 82. So this is the June 2018 Regents exam. The question was, how do I know when to use the MAVA equals MBVB formula? There's a couple of key things to look out for. Acids and bases would be the first thing. But in terms of phrasing, when you see a question that's asking you to determine the volume or the molarity, and you see the phrase neutralization or titration, that's when you know to do MAVA equals MBVB. Those are the buzzwords for that. From there, just make sure you keep all the information about the acid on the acid side of the equation and all the information about the base on the basic side of the equation. So, for example, the question says determine the volume of 0.25 molarity NaOH. NaOH is a base. It's on table L and it ends in OH. Two huge indicators that we're dealing with a base here. So, the problem stated that the molarity of the base was 0.25, and the volume of the base is what you're determining, because that's what the question asks you to do. That would exactly neutralize 75 milliliters of the acid in solution X. How do I know solution X was the acid? Because this is a data table about HCl, which right here tells you is hydrochloric acid. So, solution X's concentration is 0.1. So I'm going to plug in 0.1. I can just sit here all night and take questions. I am more than happy doing that. Keep them coming. If I don't get a question, I'll just pick another question to do. Can you go over sig figs? Yes, I will go over sig figs outside of context just because it's easier. They typically just ask you how many sig figs are in this number or how many sig figs should the answer to this question have, which you can again answer by determining how many sig figs are in the number. So let's just copy down a bunch of numbers here. 0.001, 0.0010, 1.0010. No, I'll just do 1.00. 1,000. So, no, let's do 100,150 and 0.01010. Okay. Sig fig rules. When you have a number that contains a decimal, like these, I didn't want to erase, I wanted to highlight, like these 4 numbers here. The rule is the same for all of them, and the location of the decimal does not matter. Once you see that decimal, find your first number that is not 0, the first number that is not 0, and highlight it or circle it. That's not 0, that's not 0, that's not 0, and that's not 0. From there, once you've identified the first number within your decimal number that's not 0, okay, let me repeat. Once you've identified the first non-zero number within this number that contains a decimal, you're going to start to count everything after and including that number as significant. So, these zeros don't count because they're what we're calling leading zeros. You get to your non-zero number, this number only has 1. Here we have leading zeros again. We get to our non-zero number, there's 1 number after it, this has 2. The first number we have here within our decimal is a non-zero number. Everything after that counts. We have 3. We hit our first non-zero number right there. Everything after it counts. This has 4. There is no decimal in this number. So the only number that counts is the non-zero number because there are no sandwich zeros. So this just has 1. And 100,100, again, no decimal. So when there's no decimal, zeros only count when they are sandwiched. So only these 4 numbers are significant. So this has 4. So non-zero numbers always count. Zeros only count when they are sandwiched, or they come after a non-zero number within the number that contains a decimal. The next rule they ask you is mainly about division and multiplication. If you multiply or divide numbers and they want it in terms of significant figures, your final answer should be, so multiplication and division equals least amount of sig figs. So if you were to multiply these two numbers together, your final answer should have 3 sig figs. If you were to multiply these two numbers together, your final answer should have 1 sig fig, etc. All right, I got like a bunch more text, so I have a feeling this is going to be like a Q&A session, which I love. Adic-itis, I am not going to go over because you do not need to know it. Question about percent abundance of different isotopes, you do not need to know. How does mass change in an anode and cathode? Okay, so I saw a voltaic cell on here somewhere. Right here, okay. First, let's start from scratch. How can you determine who is the anode and who is the cathode to begin with? Because that's a good place to start. You can apply the acronym REDCAT ANOX. So the cathode is where reduction is occurring, and the anode is where oxidation is occurring. Your next question might be, how do I know who's getting reduced and who's getting oxidized? There's 2 ways. The easiest way is to look at the reaction they give you, and if the charge goes down, then you're getting reduced, because getting reduced literally means to get smaller. If the charge gets smaller, you're getting reduced. So in this case, copper's charge goes from a charge of +2 to a charge of 0. Please keep in mind, no friend, no charge. So if an atom is not bonded to a different atom, it does not have a charge unless they tell you what it is. So O2 has a charge of 0. An atom always have a charge of 0. So O2 has a charge of 0. Mn has a charge of 0. But if you were to combine them to make, let's say, MnO2, then they both have charges or oxidation states. And you need to figure out what they are sometimes. So, not to kind of go off on a tangent, but this is a great time to just talk about redox. How do I figure out the oxidation states of these atoms within this compound? Keep in mind, if I were to ask you right now, what is the oxidation state of oxygen in this compound? You would just need to tell me what it is for one of those oxygens, not 2. So, for example, let me just rewrite this here. MnO2. I want to go check the periodic table for the oxidation states of Mn and O. Mn's oxidation states are 2, 3, 4, 7. Okay, that's a lot. I can't reasonably off the top of my head figure that one out. Let's check oxygen. Oh, oxygen's nice and easy. It's always -2. So whenever you're given a compound and you're asked to figure out the oxidation states within that compound, always look for the atoms who only have one option, because you're done once you get it. So if I go back there, what we would say is that oxygen's oxidation state is -2, not the fact that 2 of them make -4. 2 of them have an oxidation state combined to be -4. But if right now I asked you what is the oxidation state of oxygen, you would say -2. -4 would get you no credit. When you're given a formula, the total charge of the oxidation states must add up to 0. So if our oxygen is -4, then quite simply our manganese must be +4, because 4 minus 4 is 0. Back to my student's question. How do I know who gains mass and who loses mass? So first, we determined who was getting reduced based on the fact that copper's charge went from a +2 to 0. Its charge got smaller, therefore it gets reduced. Red cat means that copper is the cathode, which means that zinc must be the anode. So, from here, we know that electrons always flow from anode to cathode. You can even say that for number 78. State in terms of the copper electrode to the zinc electrode. Yeah, you can say zinc to copper, but if you say anode to cathode, you're not wrong. I feel like I have to sneeze. Here it comes. Yep. Excuse me. How do I know which one gains mass and which one loses mass? The cathode will always gain mass, and the anode will always lose mass. And the reason is not because the anode loses electrons or the cathode gains electrons, is because, actually this is question 80 right here. So we would say the copper electrode is gaining mass because copper is turning from an ion with a charge of +2 into an atom. Whenever the ions turn into atoms, it's going to gain mass because it's gaining electrons and getting reduced. Versus zinc is losing electrons. So zinc is going to lose mass because if you look at the reaction, zinc is going from an atom here with no charge and turning into an ion with a charge of +2. So zinc goes from an atom to an ion. So the cathode always gains mass because its ions in solution are turning into atoms into the electrode. The anode always loses mass because the atoms in the electrode are turning into ions in the solution. 7 notifications. Okay. Can you do another example with oxidation states, but when the charge does not equal 0? Yeah, and the easiest way to do that is to pick one off of table E, because everything on table E has a charge given. So, table E. Let's do carbonate. So carbonate doesn't exist as CO3 with no charge. The charge on carbonate is -2. And I got that right there. So that's what that -2 means. These are called polyatomic ions. They're ions, but composed of multiple atoms. Instead of just like O2-, it's C and O combining to make this molecule called carbonate. And carbonate itself is a charge of -2. So now our objective is not to get carbon and oxygen to add up to 0. Our objective now is to get carbon and oxygen to add up to -2. So you might remember from the previous problem, we already did one with oxygen. Oxygen has a charge of -2. So oxygen's oxidation state in this compound is -2. But there's 3 of them. So 3 times -2 is -6. So something plus -6 equals -2. What plus -6 is -2? What minus 6 is -2? 4 minus 6 is -2. And if you're not sure, you can just add 6 to both sides. That's a 6 plus 6. And you would get 4. So you can even just set up a little really basic like pre-algebra equation. You were sitting there going, okay, x minus 6 equals -2 plus 6 plus 6. Okay, carbon is +4. So if they give you a charge in the compound That just means your objective is to add up the atom's oxidation states until they equal that charge instead of 0. Same way to do the problem, nothing different. It's just you're trying to get it to that charge instead of 0. Same is true for the positive one. So if you were dealing with NH4 with a charge of +1, you would check their oxidation states. Hydrogen would end up being +1 here. So we say hydrogen's +1. I got that from the periodic table. 4 times 1 is 4. So now we got to say X plus 4 is 1. Right? Because this was positive 4. So X plus 4 is 1. So if I minus 4, I'll get -3. So nitrogen is -3. All right, got a bunch of other texts. Let's see. Yeah, okay. Number 80 in the June 2015 Regents. 80. Oh, that's 2013. Whoop. I went too far. All right, let's go to June 2015. This is 2014. All right, 2015. So, number 80. Explain in terms of ions why the gaseous reactant in the equation is classified as an Arrhenius acid. Let's just take the opportunity to go over Arrhenius acids and bases. So, we have the Arrhenius theory of acids and bases. Okay, so Arrhenius stated that acids will form hydrogen ions and bases will form hydroxide ions. And you can kind of gather that from tables K and L. So when you look at tables K and L, which is the tables of common acids and bases, you'll notice that all the acids here are like H something, H something, H something, H something. So Arrhenius said, well, acids must form H plus ions. Versus bases down here are OH, something OH, something OH. Specifically, be careful, because this is where they'll trick you, a metal plus OH. So bases, he said, well, they must form hydroxide ions. So in question 80, it said, how do we know that the gaseous reactant is an Arrhenius acid? Well, the gaseous reactant is HCl, which makes it an acid because it has H plus ions. Now, the other or alternate acid-base theory, other/alternate, so alternate acid-base theory or other acid-base theory, you can apply the acronym BAD. Bases accept H plus and acids donate H plus. So that comes into play when you have a chemical reaction between an acid and a base. And the question is always like, which one is the acid or which one's the base? Such as, and I'm pretty sure they asked it this year. So, BAD, bases accept H's, acids donate H's, specifically H plus. Please keep that in mind. I'm pretty sure there was a question on this Regents about that. Like, this is the June 2015 Regents number 25. According to one acid-base theory, a water molecule acts as a base when it accepts an H plus ion. Bases accept H pluses. Or if we flip to June 2016, like number 27, literally the exact opposite of the year before. One acid-base theory defines an acid as acids donate H's, specifically H+. Or if you go to June 2017, like question number, are you getting the idea that you're probably going to get a question on this tomorrow? Question number 45. Which formula represents the H plus acceptor in the forward reaction? So, let's see. Who accepted an H? We got HCO3 here, H2O there. H2O turned into OH. Well, that lost an H. And HCO3 turned into H2CO3. Well, that gained an H. So who gained the H? HCO3 did. So, yeah, you're probably going to get a question on this tomorrow, so just be ready for it. Polar bonds versus polar molecules. I think there was a good question on 2015 that hit both of them. And I want to say it was 2015, but let me double check. No, it wasn't 2015. I think it was 2016 that. I know it was... I just looked over it today, so I know it's nearby. 2016, June 2016, question 39 is a fantastic question that goes over both. So we can hit two birds with one stone here. All right. So question 39 on the June 2016 Regents. Let's do the easy one first. Polar versus non-polar bond. A polar bond is two different atoms. A non-polar bond are two of the same atoms. So, if you see two atoms that are different, you will simply say that's a polar bond. If you see two atoms are the same, you will say that is a non-polar bond. The true definition is non-polar bonds are between atoms with essentially the same electronegativity. But for all intents and purposes, for what you're going to see on the Regents, all the times they ask for like non-polar bonds, they're looking at the atoms that are the same. And if they're looking for polar bonds, they're just looking at two different atoms. So, the question said we wanted something with a polar bond. So, those are the same. So that's a non-polar bond. Those are different, and those are different. So those are all polar bonds. Non-polar and polar molecules is when you snap. So non-polar versus polar molecule is when you snap. SNAP stands for if it is symmetrical, it is not polar. And if it is asymmetrical, it is polar. Since these two drawings in 3 and 4 have lone pairs that they didn't draw in because they were structural, not Lewis dot formulas, or because you see those bonds bending, that means they are not symmetrical. Versus carbon dioxide here is symmetrical. It's a nice linear molecule, no lone pairs on the carbon, very symmetrical, which makes it not polar. These two guys are polar because they are not symmetrical, or they're asymmetrical. Now, I think there was also a question this year that asked, I want to say this year, it might have been June 2017, but I definitely want to go over it while we're on the polar topic, that asked which of the bonds was most polar, or something like that. Don't worry, we're going to go over saturated and electrolytes because we just have to. Oh, man. I don't want to waste time looking for it. So, if you're asked to evaluate which of these bonds is most polar, and let's just say they gave you HF, HO, HN, and HC. All right, did this on purpose. First, hydrogen bonding. If you got a question about hydrogen bonding and it wants you to identify if hydrogen bonding exists in this molecule that they give you, hydrogen bonding is fine. So, if you're asked to identify hydrogen bonding It only exists in molecules that have an H bonded with an F, an O, or a C. Not a C, an N. Wow. Let's start that from the top. Hydrogen bonding is fun. H with an F and O or an N have hydrogen bonding. If they're asking you which one of these bonds is the most polar, okay, so again, most polar bond, let's clarify that because I don't want us snapping away trying to figure this out. You want to look at their electronegativities on table S, and the further apart they are, the more polar it is. So, let's look up H and let's compare it to F, O, N, and C. So H's electronegativity is 2, and we're going to compare it to 2.6, 3.0, 3.4, and 4.0. Okay, so from my very quick mental math, it looks to me that the hydrogen and the fluorine are furthest apart in their electronegativities, which means in terms of being the most polar would be the HF bond. Not any of those. Okay, just because someone asked about it, let's go over electrolytes. Actually, let's do a quick question. Quick question. Dispersion and dipole IMFs you will not worry about. So if you ever get a question that asks you to identify the type of IMF in a compound where IMF is intermolecular force, you are going to say hydrogen bonding. Because they almost always ask about water. Why does water have such a high boiling point? Hydrogen bonding. Dispersion forces and dipole forces you don't need to worry about for tomorrow. The only type of IMF, type of intermolecular force that you need to know is hydrogen bonding. Okay, I kind of vaguely remember that the electrolyte question on June 2016 was too easy. It was. Let's pick a different year because I want to illustrate the difference by going over one that's not hard, but harder than that one. That one was kind of a gimme. Electrolytes. I think there was one last year. June 2018. Looking for a question about electrolytes. Where are you, electrolytes? Man, I'm striking out at finding questions quickly tonight. I'm just not on my A game. All right, 2015. I know they're on here. I'm looking too quickly because I don't want to waste too much time because time right now is of the essence. So, I'm gonna be fairly confident there was one on 2015. I feel like I'm gonna be right. I'm feeling pretty good. Feeling confident. Confidence is key. You're going to kill it tomorrow, okay? You guys are awesome. You know a lot of chemistry. Come on, electrolytes. Where the heck are you? Where are you? Where? All right, I'm just going to go over it because I can't find it. Electrolytes are always going to have moving charged particles. That's the key phrase. So if it says explain why this substance is an electrolyte, you say it has moving charged particles. How can you tell from a formula if something is an electrolyte? It's going to be an acid, which you'll find on table K, a base, which you can find on table L, or a salt, which is just an ionic compound, so it's going to have a metal in it. So metal in it. So when you're asked to find from a list of particles if something is an electrolyte, the right answer will be find the acid. If there's no answer choice, that's an acid. Find the base. If there's no base, that's an answer choice. Find the ionic compound. Now, I am going to find an example of that because I know it's right here. 23. Which compounds, this is a 2015 Regents, are classified as electrolytes. Don't make any assumptions that just because Mr. G just said bases end in OH, that you're going to put 4. Because you see CH3OH and you're like, base! He just said a base ends in OH. I remember. Bases need to be a metal combined with that hydroxide. CH3OH is a carbon compound. It's an organic compound, which means you can look this up on table R, and you'll find out very quickly that that's an alcohol, and therefore not an acid, not a base, nor an ionic compound. So, we want an acid, base, ionic compound. None. That's an acid. You're an ether. That's an ionic compound because K is a metal. That's an alcohol. That's an ionic compound and that's an acid. That's the correct answer. Do you need to use logs? No. You do not need to know logs. If you're ever asked to calculate the pH, so let's say I give you the H concentration was 1.0 times 10 to the negative 5. The pH is just simply the absolute value of the exponent, so it's just 5. Or, if it gave you the hydronium concentration of 0.001, 1, 2, 3, pH is 3. Don't worry about using logs. You won't need to. I mean, you definitely won't need to because those blue calculators don't have a log button on it. And some of you are in geometry right now are like, why the heck are we talking about logs? Don't worry about it. Can you go over how to write half reactions? So, yes. Let me just find an oxidation reduction reaction right here. I'm just going to copy that one. Zinc. Actually, I'll just make one up. Zinc plus copper 2 plus makes copper plus zinc 2 plus. And let's say it wanted you to write the half reactions for oxidation and reduction. So first, make sure you identify who got oxidized and who got reduced appropriately before you start. You don't want to get it wrong by just like immediately getting it backwards. I hate it if you wrote like a beautiful answer that showed oxidation of something, but you picked the wrong thing and it didn't get oxidized. So, always do reduction first, because reduction is the easiest one in my opinion. GER, gain electrons reduction. So, we know we're going to be gaining electrons. Reduction means that the oxidation state needs to go down. And remember, when they're alone, no friend, no charge. So unless they gave it to you like I just did, we need to assume the charges of this zinc and that copper are 0 because they don't have a friend. So copper's charge is going from 2 plus to 0. Copper's charge is getting smaller. Copper is getting reduced. Pull it out of the reaction. Copper 2 plus is on the left side. Leave yourself some room because we need to talk about where the electrons are going to go. Copper with no charge, you need to write that 0. Copper with no charge is on the right side. Where do the electrons go? GER, gain electrons reduction. When you're gaining electrons, you have to show them entering the reaction, aka on the left-hand side of the arrow. So your 2 electrons are going to be over here. Now, all you have to do for zinc is the exact opposite that you did for copper. Zinc starts at a charge of 0 and turns into zinc 2 plus, 0 to 2. That's 2 electrons being lost because for oxidation you say Leo, lose electrons oxidation. That's the basics behind half reactions. Can you go over the main things we need to know about organic reactions? The main things that you need to know about organic reactions is you need to know the organic reactions. So, I need room. There are 7, I want to say, organic reactions. We have addition. Addition's kind of easy to spot out. You'll have some hydrocarbon, usually an alkene, because an alkene means it's unsaturated. We'll go over that in a minute. And you're literally just going to add things to it. That's addition. There was 2 chlorines not attached to it. Now there's 2 chlorines that are attached to it. I'm going to turn the light on. It's starting to get dark. Okay. Addition. That's that. Yay. Substitution. Substitution is when you are doing just like a 1-for-1 swap. So, while addition occurs on like alkenes, substitution occurs on alkanes. So that means there's all single bonds. So you would add Cl2 again, but this time only one of them would be added onto the compound, and one of the H's would just swap out. So you did a Cl for hydrogen substitution. It's literally like substitution in any sport that has substitution in it. A player comes in, a player pops out. There's combustion. Now, combustion, if you ever forget, are like the first 5 reactions on table I. So you can always check table I. Combustion is when you take any hydrocarbon of any formula, CXHY, and you combine it with oxygen. It's always going to make carbon dioxide and water. So anytime you're reacting hydrocarbons are compounds that only contain hydrogen or carbon, and you mix it with some oxygen and some fire, and you're going to get carbon dioxide and water. There's esterification. The first thing you should probably figure out about esterification is that the product will have an ester. So you can look up the general formula the functional group on table R to make sure you can recognize what an ester looks like. And it's always going to be an alcohol and an organic acid combining to make an ester and water. So you can look these up on table R, but esters always have this functional group, a C double bond O. Alcohols have OHs. Organic acids have C double bond O with an OH. Water's water. So, how do I know this was esterification? Because you formed an ester. If it doesn't give you it in pictures and gives you it in words, it's always an alcohol plus an organic acid. Or vice versa, an organic acid plus an alcohol. You'll always get the same answer, no matter how you react them. All right, saponification. Biggest thing you need to know about saponification is that makes soap. So when you see saponification, just think soap. If you see soap, think saponification. Fermentation is when you take a sugar, like glucose, and you use an enzyme. Typically, they'll give you zymase. That will make alcohol plus carbon dioxide. So that one is fermentation. And then there is polymerization. So polymerization is when you take numerous monomers, is what the word is, but numerous small things. So usually you'll see like CH2 plus CH2, and it might give you like ... makes one big CH2 molecule. So you'll usually see something with like little ends or big ends floating across the reaction, where the ends just mean like any large number of these molecules combining together. Your next question might be, do I need to know all of these for tomorrow? This comes back to what I said at the beginning. I cannot predict what they will ask. I can only tell you what they might ask. They will probably ask for one of these. That's life. Can you go over acids and bases again? Be more specific. That's an entire unit. You are correct, student, that pointed out that question 74 on last year's Regents was evil. I think the word you're looking for was dumb. It was probably one of my least favorite questions of all time. It's just stupid. You literally had to get the molecular formula for this. So I'm just laughing thinking about how dumb it was. So you had to sit there and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You get the idea. You had to count all the atoms in this freaking formula for some reason. They thought that was like a question that was worth asking. Quick little bonus question, pop quiz. Maybe we'll get like a candy bar tomorrow. You won't. What do you think happens when you read that formula too quickly? What do these C's start to blend together as? Think about it. It's question 74. It's probably starting to get hot in that gym. This is literally the last thing in your way between summer and school. You hand this test in, and you're at summer. You're reading this quickly. What are those C's going to start to look like? Oxygens, because you're going to start closing that tiny, tiny little gap that makes it a C. All of a sudden, a couple of those C's start to look like O's. And you're not going to get the point because you counted wrong. And you get your score back, and you get a 98 because you couldn't count. I hated that question. It was so dumb. I think, did I do question 23 from June 2015? Because I don't remember at this point. I think I did. Let me check real quick. Yeah, I did. Okay. Another electrolyte one. June 2017, question 83. Oh, that one was explained using words. Why we had an electrolyte. What year is this? 18. June 2017, 83. And we're going to end up going over one on that question as well. So 83, explain in terms of particles why that can conduct an electric current. That's when you go moving charged particles. So keep in mind, substances in the solid state, like NaCl as a solid, cannot conduct because the particles cannot move yet. So ionic compounds only conduct in the liquid state or when you put them in water and they become aqueous. NaCl as a solid can't conduct because it does not have moving charged particles. But 85 I wanted to do because this one had interesting answers. So first, generally speaking, as the H plus / H3O plus, H3O plus is just hydronium. Hydronium's on table E, so don't freak out if you just see this H3O plus. You're like, what the heck is that? As that goes down, the pH is going to go up. And obviously the reverse is true. If those go down, then the pH will, if those go up, getting ahead of myself, the pH is going to go down. So that's step one into tackling question 85 on the June 2017 Regents. The next thing you have to keep in mind when you're doing this is that as the H plus / H3O plus move up or down by powers of 10, so let's say like 10 to the x, then the pH, again, depending on what's happening, is going to go up or down by one step. One step per x. Meaning, if H plus is increased by a factor of 1,000-fold, 1,000, that's 10 to the third, then the pH is going to go down 3 steps. So every time you multiply the hydronium concentration times 10, the pH is going to change by 1. So 1,000 is 10 times 10 times 10. If you say that the concentration, or let's say The pH goes from 3 to 4. Then the concentration of your hydronium went down by a factor of 10. So when you look at the question 85, and again, this was like the last question on the Regents. This was like a huge missed question that year. I had the pleasure of grading it. 10 times fewer hydronium. So hydronium is going down times 10. Then the pH is going to go up plus 1. So it's going to be 3.4. Can you go over exo and endo with heat of yeah, we sure can. All right, let's draw some potential energy diagrams. Let's make up some numbers. Let's say this is a hundo, this is 150, and this right here is 50. Okay, first, activation energy. Activation energy is the difference between the Hill and the heat of the reactant, which is where the graph starts. So the activation energy from this reaction would be 100. I know I'm unitless, being a terrible scientist. Time is of the essence. You would say this is an endothermic curve for two reasons. One, it starts low and ends high. Two, when you do the heat of the reaction, aka your delta H, so your heat of the reaction, you always do products minus reactants, which in this case is going to be 100 minus 50. And since you get a positive answer, you would say that this is endothermic. So for whatever reaction this is, you would say those 50 kilojoules would be a reactant, because endothermic curves, or I should really say endothermic reactions, involve heat being absorbed / heat entering the reaction. Versus an exothermic curve will look something like this. Start high and end low. So when you do the same thing, when you do the heat of the reaction for this exothermic curve, you would do products, which is where you end, minus the reactants, and you would get a negative number. So a negative delta H means you're exothermic. So if you were to write this reaction, you would put the heat on the product side, because in exothermic reactions, heat is exiting. Big question we get is, why is it negative there but positive here? It's not positive there. It's just convention in chemical reactions to write everything with a plus sign, and then you just have to evaluate what that sign means relative to what side of the equation it's on. So since heat is exiting this reaction, you would say it's exothermic, which means it has a negative delta H. You can confirm that information on table I. So when you go to table I, it tells you right there, a minus sign indicates an exothermic reaction. So you'll always be good. Would you kindly reiterate the ideal gas laws? So what you're trying to say is not the ideal gas law like equation, which is Pivner. I think it was a fine question. I'm just being semantic. You want to say, what are the behaviors of an ideal gas according to the kinetic molecular theory? So, ideal gases. A gas approaches ideal conditions at a high temperature and a low pressure. 1. Random straight line motion. 2. Super far apart. Super far apart where the molecules have a very, 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 very tiny volume. 3. Energy will always transfer on a collision. I always like end up drawing a blank in the middle of these for all the time. High temp, low press, random straight line motion. They're very far apart. Super small volume. Energy transfers upon a collision, and there's no attraction. So the molecules do not attract each other. I'll just say collide. That should be about it. So those are the principles of ideal gases. They occur at high temperature and low pressure conditions. They move in random straight lines. They are very far apart due to their very small volume. They transfer energy when they collide, and they do not attract each other. That is a popular question. They like to ask about it. Okay, I'm going to say a few more minutes. If I don't get any more questions, I feel like I've done a lot. I was going to cover like certain things, but you ended up asking really great questions, so I didn't feel like I need to like cover what I wanted to cover necessarily. Not that I didn't cover what I wanted to cover. I ended up covering a lot that I wanted to cover because of your awesome questions. So couple more minutes. I'll get this on my YouTube channel as quick as possible for your super, super, super unbelievably late studiers. But you do get a good night's sleep tonight. If you're not going to get it by 9 or 10 o'clock tonight, just don't worry about it. You probably do know the right answer. You're just psyching yourself out right now because you've been taking finals and Regents for like a few straight days. You know, you had your flax today. You had those lovely math Regents on Friday. Just like go relax, all right? Have a great night. Text me on Remind if you have any questions. You're the best. Thank you for being great students. Questions, questions, questions. There's a bunch of other videos on my YouTube channel you're more than welcome to check out that go over other questions we might not have covered tonight. Where's the pup? She's been requested. Harper.
Hey, go get that. Yeah, you're gonna have to get a treat.
Harper, you want a treat?
She just picked her head up and then put it back down on my chest. Go get him. Go get him.
Come here, girl.
Oh, Dad, get
Come here, come here.
He's running.
Get up, girl. Get up. Get up. You can do it. Up. Yeah. Good girl. Where's the best girl? There you go. There's Harper. I think she popped in. Let's see. Yeah, I see your head. Hold on. Say hi, Harper. Harper, look up here. Say hi. Hi. Yeah, you're a good girl. Yeah, the best girl. All right, guys. It looked like my viewership just went up by like 5 when Harper came into the picture. I think that's it. I don't think I've gotten much more. Oop, just kidding. Someone's chiming in with a question. Love it. Love it. All right, let me get my dog out of here before she just stares at me, begging me for more treats. Harper, here you go, you go. You go, you go, go. Nice, see ya. Okay. She's all hyped up now because she got a treat. I'm going crazy. Okay, can you go over how pressure and temperature, blah, 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 equilibrium? Okay. The question was equilibrium. First thing to know about equilibrium, okay? Equal rates, constant concentration. All right? Just remember the constant goes with the constant. Constant, constant, constant. Constant concentration. It's alliteration. There's an English term. Hope you use that on your English Regents last week, you juniors. And equal rates. So when you hear equilibrium, we are talking about equal rates, constant concentration. Okay. Let's just make up a reaction here, and I'll do as best as I can to like get all of it. 2NH3. Of course I ran out of room. Why would I write it small enough? Let's say heat's over here. Okay. First, in terms of concentration of stuff, if you increase something, let's say H2, you always shift away from an increase in the concentration of a compound in the reaction. So this would shift to the right. You would increase the amount of NH3 and heat you're producing, and you would decrease the N2 because N2 and H2 need to react in order for NH3 to form. The H2 would also go down. Okay. If you were to decrease H2, the reaction always shifts in the same direction as a decrease. So in this case, the NH3 would go away to help make more N2 and H2. Because again, this is what you're doing, and this over here is how the reaction is responding. The reaction can't just make more H2 out of nothing. The only way it knows how to make more H2 is to split up NH3. Conversely, when we increased H2, you can't just open the container and just let the H2 out. The only way the reaction knows how to get rid of the H2 is to combine it with N2 and make NH3. Heat/temperature works the exact same way. If I were to increase the temperature in this reaction, since it's an exothermic reaction because heat is a product, it would shift away from the increase, which in this case would be a shift to the left, which means our NH3 is going to start disappearing as the reaction is making more N2 and H2. A decrease in temperature would do the opposite. A decrease in temperature will always shift in the direction of that decrease. If temperature goes down, this would shift to the right side. N2 and H2 would start to disappear as it makes more NH3. Now, since all of these substances in the reaction here are gases, let's talk about pressure. All right, NH3 is a gas. As pressure is increased, it always shifts in the direction of less gas, less moles of gas, which in this case would be a shift to the right because the left side has 1 plus 3, which is 4 moles of gas, and the right side has 2 moles of gas. So an increase in pressure will always shift in the direction of less gas, and a decrease in pressure will always shift in the direction of more gas. Any other questions? Ooh, okay, so it's the end of the year. You guys are going to be fine tomorrow. I'm dead serious. Most of you that are on right now, which is probably a decent chunk of my honors kids at this point, you're just worried that you're not going to get 100. I have faith that all of my students are going to do super well. All you need to do is take your time. If you get stuck, flip through that reference table. You'll be surprised what you find in there. you can try asking a question. No one's going to help you, but sometimes maybe you just need someone to talk to in the Regents. Raise your hand. I had a student, I did, but Mrs. G had a student raise their hand during the Algebra 2 Regents, just say, I got this question, Mrs. G. If you just need a little pick me up tomorrow, raise your hand. I'll try to come by, give you a little fist bump, let you know that you got it, because you're going to crush it tomorrow. You got to take your time, read the question completely, read all the answer choices, use some process of elimination, please. That'd be great, because sometimes you just read the first answer choice and just assume that's the right one. Read all of them, cross out the wrong answers, give yourself the best shot to get it right. There is nothing on that test that you don't know. It just might not be in a form that you've seen before. Take a deep breath, say, he's gone over all the information with me. I have retaken almost everything. He has given me the opportunity to do a lot of practice, provided me with flashcards for this test, Castle Learnings. What is this? The 6th video I've done for this year, just for the Regents. I know what's going to be on here. This is you right now. You know what's going to be on there. You just need to convince yourself that you're going to get it right, which you will, okay? You guys are awesome. It's been a great year. It's had its ups and downs, obviously, but mostly it's been great. I'm going to miss you guys. Just make sure you say goodbye to me on the way out tomorrow. Don't leave me hanging. And I will see you at 7:45 in the morning, because your test starts at 8. Had a little scare today. Heard someone throw out the word noon. Please don't do that. I had a kid show up almost, I think it was at least an hour late last year, because what he told me was some kid on Fortnite told him it started at noon. Don't listen to this kid on Fortnite. Listen to your teacher. You know who knows when your test is? Me. 8 a.m. is when it starts, so get there a little bit earlier. Bring a pen. Don't bring a graphing calculator. You're going to do great. I'll see you tomorrow. Good night.